Hi, my name is Ben Oberkfell. I'm an Android developer with the New York Times. I work on the mobile crossword app. And before the Times, I've worked at a few companies like American Express and Jive Software and doing Android there. And before I discovered Android, I used to work in biotechnology. I worked on the Human Genome Project and in cancer research. Previously, like all great serial dramas, we have a sequel. At DroidCon New York in 2016, I gave this talk on fingerprint authentication. So in this talk, we covered things about how to detect fingerprint hardware, how to do UI design for the fingerprint flows that your users see, and then also how to log into remote services using a fingerprint-attested key pair. So the idea was if you've ever used SSH to log into a remote service, it's just like that, but for your app. So if you want some introductory information on the fingerprint package, there's a place for you to check out as well. And then also, I had some appearances on the Fragmented podcast back in February, where we kind of did some free-form chatting about what's under the hood. And then there's a Cliff Notes version of it all when I was on the Android Dialogues YouTube channel as well. So there's plenty of other refreshers as well for you to check out after this. So today, however, we're going to talk about how to use Fingerprint for encrypting your local data while also protecting the keys for doing so. We're going to do a brief recap about how to engage the Fingerprint API within your own app. And then we're also going to talk about some risks you might encounter with fingerprint-backed keys and how you might want to mitigate them. So the example app we have up on GitHub is a diary that encrypts its entries at rest. So you can use a password or a fingerprint to unlock the entries. And so if you happen to end up wearing gloves or you get a new phone, you're still able to get at your data. Show of hands, how many people have used like a 1Password or LastPass on their Android phone? Cool. So you're kind of aware of this flow where you key in a password to unlock your database, and then you have the additional security of your fingerprint. So how this example app works is you have a password that doubles as your recovery password. You enroll your fingerprint to bypass the password. And so we'll play the video here. So we'll go ahead and check this box here for hang on a second. I don't know why the video is being slightly. Oh, there we go. OK. So we're going to use most insecure password ever, password. And then we're going to scan our fingerprint, and we get our data. Now, when we return to the app, on our next visit, we're prompted for fingerprint authentication. And so you can go straight back to your private data. So here we're going to go and just scan, and away we go. So we kind of have a design problem here. We want to be able to encrypt our secret data. Maybe we have our passwords, our personal thoughts and feelings in our diary. Maybe we have top secret UFO documents, something we have that we want to encrypt. We also want to hide our encryption key from attackers. If you were at Marco's talk yesterday about reverse engineering and attacking Android applications, he brought up some great points about making sure that secrets and the like are not exposed. So we want to make sure we hide our key, but surely we can do better than something like this. We don't want to leave it out in the open. We also want to free our users from a password, at least in most instances. I preach to the choir here when I say that passwords suck and that you don't want to use them all the time. So a fingerprint is a great convenience for that. So what we really want is something like this. maybe a fingerprint safe instead of a key lock. So let's get to work on building what we have. So who in the room is familiar or has looked at the Android compatibility definition document? So 2 in the room, and I know you are involved in porting Android, so yeah. For everyone else, if you haven't seen it, it's actually kind of an enlightening read. It's essentially, if you're porting Android to a new device and you want to get the Play Store and the Google services on this, this is going to be your Bible. And it's also a sort of source of truth for developers to be able to review this and know what they can expect in a device when they're developing for a particular iteration of the Android platform. So, while vendors are free to do some things with the platform, there are going to be some constants that you hopefully can rely upon as a developer. And one of the things that wound up in the CDD for version 6.0 of Android are some rules around fingerprint sensors. So if a device has a secure lock screen, which they all do now, they should have a fingerprint sensor. This is a good thing. Now, if the fingerprint sensor is there and there's not a private API that only the vendor can use, if they're actually going to map to the Android SDK's fingerprint library, there's some additional rules around the fingerprint sensor. They need to have a hardware bat implementation of its key store. And it uses a trusted execution environment for doing much of this work. So one thing that's kind of obscure about Android that you might not know about is that there's actually a separate operating system running in a trusted environment on the phone. It's called Trusty, and there's some components there for doing your PIN and pattern authentication. The matching takes place under Trusty, and then also some of these sensitive crypto operations happen in this trusted environment as well. And the idea is with the trusted environment is that sensitive keys never leave the friendly confines of the trusted environment. So there's sort of a, some holes punched through the trusted environment for APIs here so that you can do operations in the secure world without exposing that data outside. One thing that Android did in version 6.0 was they added AES encryption to that secure world. So we're going to be using that. So if we look at what we have here for the sort of the service stack in Android for the fingerprint library, we have the trusted world, which is where the fingerprint hardware actually talks to, and the matching takes place within this trusted world. And then our app is this far thing off here in the corner, way out of the way from where any of the real magic happens. We talk only to the fingerprint manager, and then it's Android all the way down. And so we also talk to the key store for doing our gathering our encryption keys that we're going to use, and then all this happens under the hood for us in a secure environment. So our fingerprint manager is going to be our primary point of contact when we're working with the fingerprint SDK on Android. So if you look at the fingerprint manager class, this was added in API 23. It has some simple methods for interacting with the fingerprint services. Since it's in 23, they've given us a bone in the support library so that you can avoid having to do things like runtime version checks to avoid getting the SDK and the compiler to barf at you. So there's Fingerprint Manager Compat that gives you much of this in a nice backward compatible layer. And in Android versions before 23, you get a no op instead of any real operation, since you don't actually have the fingerprint sensor. So Fingerprint Manager has 4 methods. One is we're able to see if our fingerprint manager hardware or fingerprint managed hardware exists. So is their hardware, and then also are fingerprints enrolled. And this is able to help you decide whether to present in the UI, should I show the fingerprint screen or not. In our example app, if neither of these match, we just don't show that checkbox that says use fingerprint. Maybe in a more robust implementation that's beyond a toy, you might want to actually say, hey, I see you have fingerprint readers. You don't have fingerprints. If you go enroll one, we can make your life a little easier. So the other this is going to be your central point with the fingerprint manager, which is the authenticate call. And so this takes a crypto object, which is essentially a wrapper around some of the Java crypto primitives, and then also a callback that you get when your authentication with the fingerprint reader either passes or fails. And so this is what we're going to demonstrate here in actually talking to the reader and doing the authentication. So the first step to actually doing what we're going to do is we need to create a key that is backed by the fingerprint scanner so that it can't be used when the fingerprint scanner, it can't be used without the user's consent. So we're going to use the key generator here with an AES key, and we're using the Android key store provider to do this, and that's available from API 18+. And then here is the kicker. This line in the builder sets that this key can't be used without authentication. And so anytime you try and use this key without authentication, you'll get a key store exception. So when you prepare to use the key, we're going to go ahead and instantiate a Java cipher object for wrapping that key so we can use it. So we'll load up the key, and then we'll either decide if we're going to do encryption or decryption and set the mode on the cipher. And if you try and use this cipher before you authenticate, you would get a key store exception from Android. Now, one salient point here is that it's important to retain the initialization vector that's used during the encryption process, or else the data gets unrecoverable at decryption time. And so let's take a little bit of a side quest here, if you will. What exactly is the initialization vector, and why should we care about it? So AES, the Advanced Encryption Standard, is a blocked cipher. It takes in 16 bytes of clear text and gives you back 16 bytes of encrypted text. Now we run this in cipher blockchaining mode, hashtag blockchain. So each block of clear text is exclusive ORed with the previous block before it gets encrypted. And so the idea here is that you have an inductive process from A to Z, so that if I have repetitive values in my plain text stream, they don't become repetitive values in the crypto stream. So you need to prime this value somehow, because the first block has to be XOR'd with something. So the initialization vector is a 16-byte block that's random data that gets generated every time you encrypt. And so in order, part of the idea here with generating it every time is that you want to prevent a situation where for every invocation of the encryption, the same plain text equals the same ciphertext. So we go ahead and we grab the IV from the cipher that Android generates randomly for us, and then we save that in a shared pref. And then when we go to decrypt, we go ahead and plot that back out and use that in initializing the cipher for decryption. So let's go back to this method here for authentication. So now that we have our cipher, we can go and get a crypto object that wraps it. And the crypto object, like I said, wraps these Java crypto primitives. So you can wrap a cipher. If you're doing public key signing, you can also wrap with a signature object from the same Java crypto package. But we're going to use a cipher today. And then we're going to call authenticate on the fingerprint manager with that crypto object. And the other thing you see here is the cancellation signal. So in a normal app, you're obviously not going to new this up right here, right alongside it, because you're going to want to use this in your UI flow as you want to cancel this operation. So maybe someone hits cancel on the fingerprint reader dialog. Maybe you back out of the activity. You want to cancel on it on pause. Whatever your use case really defines. But definitely one point I'd seen is to make sure that if you go into the background that you cancel, because I've seen apps that effectively end up hijacking the fingerprint sensor after they go in the background. And so when you end up finding yourself back at your lock screen, your fingerprint won't actually unlock your phone because the events were going to your app in the background. So I don't know if that's been fixed. I remember seeing it on some early versions of Android M. But once you get your fingerprint authenticated, you're in your callback here, where you get a crypto object back from your result. And we're able to grab that blessed cipher object now that it's been authenticated and use it to decrypt. And I've kind of elided some of the other callback methods here for brevity. But if you were to fail your authentication, you also get two different methods for failed to receive messages from the Fingerprint SDK to present to the user. So one thing that's nice is that if the vendor has their own messages for you scan too fast or your finger is dirty or things like that, the vendor can give you a localized message that's specific to the hardware implementation that's on the phone. But for right now, we don't really care about success. So we're going to grab that cipher out and decrypt. And so finally, now we can use this value here, get our message we want to decrypt, and we'll say do final, which is a one-shot decryption method on the cipher. And we'll get a byte array back that represents the value. So now we've talked about how to actually encrypt something with the fingerprint reader. Let's talk about a caveat here you might run into. And that is called key invalidation. So here's the scenario. I've gone ahead and set up fingerprint lock screen on my phone, maybe like right after I bought it, took it out of the box. Later on, I've downloaded fingerprint apps like my diary, or maybe my bank app, or my doctor's patient portal app, things like that. All these things have fingerprint authentication tied to them now. So now I'm at a party, and I've got my phone hooked up to my boombox. And I have a really trusted best friend who has agreed to run Spotify on my behalf so I can go and mingle at my party, and they can go and use my phone to manage the playlists and get past the lock screen. So I didn't want to give them my PIN number, so I just put my fingerprint on it. Should they be able to use their fingerprint in apps that have been trained to use mine? It's a really interesting question. I mean, at some point, the fingerprint is used to unlock the device, but it's also now the source of truth for other apps. And so it puts you in a quandary here of how to think about this. And luckily or unluckily for us, the Android platform has decided to kind of make that decision for us. So there's some circumstances in which the keys can that are fingerprint authenticated can be invalidated. So if you remove your lock screen altogether, or you take away all your enrolled fingerprints, keys will be invalidated. On Android M, if you enroll a new fingerprint, keys are invalidated. And then now from Android N, this is a flag that you can set on that key generator spec. You can say set invalidated by biometric enrollment and say false here. Now, Android M is not going away anytime soon, so you're going to have some strategy to manage this. But if you try and use it, when you try and initialize a cipher with that key, Android's going to be, tell you, oh, no, key's permanently invalidated, and you get an exception right there on the spot. So at that point, once some of these things have happened, the key is totally dead to you, and any data you had encrypted with it, inaccessible, gone. So how do we work around this? So maybe this matters to you, maybe it doesn't. Does losing the data not matter? Maybe it can be recovered from the network. Maybe it can be recovered from user input. For our purpose and our diary, we definitely don't want to make the user have to re-input all their personal messages again if they add a new fingerprint. And we also want to make sure that since this is a private diary, we might, for our demo's sake, we don't have a network service to back up to. So we got to have some kind of plan. So let's think through how to deal with invalidated keys. So let's look back to our example that we've seen in apps like 1Password or LastPass. So a recovery passphrase would be pretty helpful as a mitigation strategy here. And luckily for us, there's the password-based key derivation function that lets you essentially generate an encryption key right out of a passphrase. And so you'd find this out in the world. If you use Signal, there's a option in there to encrypt data at rest, and it asks for a passphrase, and it's using this method under the hood. And you can actually look at their open source code on GitHub to see how they're doing it. It's also been noted that LastPass does it, and 1Password also has a blog post talking about how they're using this algorithm for generating their encryption keys for your LastPass store. So the end-to-end flow that we would use here with this is that first we would prompt our user for their password. Then we're going to go and take that as an input to the key derivation function and generate an encryption key. And then we're going to initialize our data store for our diary with that key. So in our example, we're using Realm as a data store. It actually gives you the option to pass it a encryption key string. Another kind of easy way to get this going for you as an encrypted data store is their SQL cipher, which is a SQLite implementation that does encryption at rest. And then one thing I noticed, if you're into the new Android architecture components, Mark Murphy from Commonsware has an open source. It's kind of embryonic right now, but what's pretty promising. He's got an open source bridge between SQL Cipher and the Room ORM library that just came out at I/O. So that's pretty cool. So we're going to initialize the database with that new key. And then we go to encrypt that key with what was one that was fingerprint authenticated. So we'll derive our key. The key derivation function has a set number of iterations that you run through, and this is a difficulty factor for making it tougher for someone to break this algorithm. So by adding multiple iterations, you end up increasing the complexity necessary to brute force it back out. So we want to generate a 512-bit key because that's what Realm wants for it. And then we're going to go ahead and pass in a salt, which is a randomly generated value to make sure that the same input password from the user doesn't give it the same input encryption key. And then we'll go ahead and generate this value and give it back an encoded byte array that would use in Realm. And so one thing that's important here when you do this is that after you successfully generate the password, you want to make sure that you persist this salt somewhere so that you can use as an input to this function again the next time the user wants to open up their diary. So otherwise, if you're randomly regenerating it, they'll get in the first time and then never again afterward. So we'll initialize the database. Here's how you do it in Realm. Basically just set up a configuration with the key and then try and get an instance of the database. Now your first time in, this is obviously going to pass. It's going to bootstrap the database with that encryption key, and it's off to the races. For second time and so forth that you're opening, you give it the key, and then you need to open the database and test to see if it throws when you do so. So if you get an access error exception from Realm, you get kind of an indication here that you've probably been using the wrong key to unlock the database. So knowing that the key is good, that we've successfully been able to unlock our Realm, we have that key sitting, sitting there, so we can go and get a cipher for the purpose of encryption. We can authenticate with the fingerprint to unlock the key that we're going to use to encrypt the Realm key. We're going to use the cipher to process that and get an encrypted version of the Realm key. And then we can persist that value locally. In our example code, we just have that in a shared pref. Now, when you return to the app, and you saw it just prompt for the fingerprint and take you right there, we're going to grab a cipher for the purpose of decryption. We'll do a fingerprint authentication to unlock that key. We'll decrypt out of the shared pref and reveal the DB key that we then pass over to Realm. So it's kind of two different flows, in and out. But one way or another, you have the ability to open the database with either something the user knows or something that is stored securely on the device that is encrypted at rest. So one thing to concern yourself with too is migrating data to another device. It's that time of the year when everyone's buying the hot new Pixel phone and they want to migrate their data and not lose anything or not having their apps break. So I have my private diary I don't have private diary.biz that runs a network service that you can sign into and send your data to the cloud. So I need to have the ability to migrate my data to the local data to another device without any too much trouble for the user. So kind of have to think about what content you're going to pass forward to the new device. And here's kind of a table of what's good to keep and what not to keep. So obviously you want to encrypt your database, keep your encrypted database because that's the core of your data store. You also want to keep the salt that you used for the key derivation function. So that way the next time that the user signs in on their new phone with their original password, they're able to unlock the database and then go back through the fingerprint enrollment flow to set up the fingerprint again. You don't want to keep the encrypted database unlock key. It's tied to a key that you can't get because it's stored in hardware on the old phone. And then you also don't want to keep the IV from the cipher that you use to encrypt that value either, because it needs to be unique every operation. So one thing that if you look at the Android, if you're using Android's auto backup framework, which since you're storing encrypted values for your data stores, if you do use Android backup, you're not exposing anything in clear text. They actually have some documentation here on how you can exclude some of these values from being auto backed up. So if you have a separate shared preference file for your IV and your encryption, the encrypted database key, you can exclude those from being backed up so that if your user restores from another on another phone, you don't have to really do any sort of involved process of trying to determine the state of the system. You just see that those values aren't there and you're able to just bootstrap the process again. So with that, here's a link to the GitHub page again and a smaller URL for saving or tweeting. Here's my Twitter account. I thank you for coming out, and I'll open the floor for questions.